So let's talk about some cases where we see entropy, an increase or a decrease in entropy. So wood burning, obviously there's fire involved. Obviously we are destroying things. Obviously there's heat being released. This is going to be an increase in entropy. Water freezing. So the water molecules are rapidly changing, okay? And they're rapidly moving, and they have a high velocity and high kinetic energy. When we freeze them, we slow that velocity down. We reduce the kinetic energy, okay? But be mindful that we are decreasing the entropy of the water. But in order to freeze ice, we have to go ahead and put in a freezer, for example, and that requires energy. So in the process of making ice, in the process of us decreasing the entropy of the water, we are increasing the entropy of the universe. Okay. Snowball melting is the opposite. This is going from a state of low kinetic energy to high kinetic energy, so we're increasing the entropy. Remember, entropy is disorder in a system. The change in entropy is heat over temperature. An iron nail rusting, right? We are disorder, it's chaos. This is chemical entropy. You're going to learn more about this in chemistry. And bread is put in the freezer. We're stopping the decay process, right? This is the idea behind cryogenics. You might want to look into cryogenics, right? The idea of putting somebody into a freezer, or freezing something, right? Freezing cancer cells so they stop their progress. The idea of freezing specimens or animals, right? Or in this case, the idea of freezing bread to make it last longer. That's what a freezer is really for. It's for decreasing entropy. So you could rename the freezer entropy decreaser. Okay, here are 4 pictures. You'll notice that this one has a pattern where most of them are up here. This one has some pattern up here, and some spread around here. This one has mostly down here, but this one doesn't have a pattern at all. It's spread out everywhere. Okay, so C is the one that has the most entropy out of all of them. All of them have to a certain extent entropy, but C has the most because it's not as predictable. Potential energy. If we go ahead and were to drop this rock, right, we want to find the change in entropy. The temperature given is 293 Kelvin. Remember, make sure that when you do entropy problems that you have temperature in Kelvin. Q, however, in this case, recall that Q, based on first law of thermodynamics, could be equal to kinetic energy. Based on conservation of energy, kinetic energy could be potential energy. For this problem, because a rock is falling into a lake, we propose to you, this is not always the case, but we propose to you that the Q could be the potential energy. So if you go ahead and do that 1,000 kilogram mass times the 9.8 meters per second squared times the 125 meters that it fell, you're going to get 122,500 joules. And your change in entropy will be 4180.9 joules per Kelvin. So this is a case where knowing your energy relationships helps a lot.
Perfect.
Finally, problem 5, specific heat. Here we have a styrofoam cup. Water is given in grams. We need to change to kilograms, right? 0.125 kilograms. Celsius, it's fine. Well, we should probably, if we're doing entropy, we need to make this to Kelvin, right? The heat, right? So Q is equal to M times C times delta T. The mass being 0.125 kilograms. The specific heat of water in our notes is 4186 joules per kilogram Kelvin. And then the temperature change, right? If I convert these Celsius to kelvins and then subtract them, the delta T ends up being 80 Kelvin. But we're looking for the entropy, right? We're looking for the entropy, the change in entropy. So that's going to be delta S is equal to Q over the temperature, right? So this is going to be that 41860 joules. And of course, this is me changing the 20 degrees Celsius to Kelvin. That 142.79 joules per Kelvin. For the last problem we just did, write down some observations that you noticed.
That's all there is to it.